Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on impedance matching. On my previous video, I have discussed basically the advantages and also the disadvantage of a lambda over 4 transformer versus a multi-stage transformer. On that particular video, I discussed when we need to have a multi-stage transformer. Basically, the key idea is to increase the bandwidth. So hence, when we actually need a larger bandwidth, then we will consider to use multi-stage transformer. So this video, I'm going to discuss how can we actually design a multi-stage transformer using binomial transformer for impedance matching. So basically, this will be the objective of this video. How can we actually design an impedance matching using this binomial, which is also known as Butterworth, in order to achieve a multi-stage transformer? This will be the part 13 series discussion on impedance matching. So guys, if you're keen to know more about impedance matching, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on impedance matching. This is my email. If you have any question regards on this discussion, please drop me an email. Or if not, I actually strongly recommend that you guys send through your question through comment. This is because, frankly, I hardly check this email. So guys, if you want to have a faster response, please send it through comment. Guys, also, you can also send through comment. How can I actually improve the quality of this channel? Thank you. And guys, I also need your help to like this video. And also, for those who are new to this channel, please consider to subscribe and turn on your notification bell. Let's continue. There are two common ways to design a multi-stage transformer. The first way is to use the binomial, which is also known as the Butterworth. So basically for this video, I'm going to concentrate on this binomial to design this multi-stage transformer. Another method is to use this Chebyshev. Let me go through the difference between binomial and also Chebyshev method to design a multi-stage transformer. For binomial, the key advantage of the design, it will have the flattest response at the center frequency. If you take a look on this frequency response, you can see that when n is equals to 1 or n equals to 2, etc., you can see that they basically match at the center frequency. So hence, basically for this binomial, the design will have the flattest response right at the center frequency. As for Chebyshev, firstly, for Chebyshev, basically you need to tolerate some constant ripple over the bandwidth. As you can see from here, for n equals to 1, you will not have any ripple. But anything more than 1, you can see that you actually have some undesired effect, which is the ripple. So basically for this method using Chebyshev, you must be able to have some tolerance in order to have some ripple over the bandwidth. However, the key advantage of using Chebyshev, it will have the largest bandwidth for a given acceptable level of reflection coefficient. So from here, you can clearly see that, let's say n is equals to 1. Basically, for Chebyshev or binomial, they are almost the same regards on the frequency response. However, when n equals to 2, equal to 3, equals to 4, when this n increase, the number of session actually increase. Like for example, this n, which stands for the number of session. When you actually increase the number of session of the multi-stage transformer, you can see that for Chebyshev, the bandwidth is actually also increased. But for binomial, you can see that it has slight effect in terms of bandwidth. But for Chebyshev, the key advantage is you're going to have the largest bandwidth in order to accommodate impedance matching. So basically, these two diagrams here highlight the key difference between using binomial to design this multi-stage transformer or when you're going to use Chebyshev to design this multi-stage transformer. In short, basically for Chebyshev, you actually want to achieve a larger bandwidth. As for binomial, you actually will have so-called the matching at the center of frequency, you won't have any ripple at the bandwidth. So basically, this will be the key difference between these two methods. For this video, I'm going to concentrate on the design of binomial, okay, which is the Butterworth method. The maximum flat transformer is a multi-section step-impedance transformer where the sections are all 1/4 wavelength at the center frequency. Okay, so basically for this multi-stage transformer, okay, basically you have many stages. For example, you have 3 stages. Okay, every stages, they all have this quarter wavelength design at the center frequency. So basically, this is what it means by this synthesis. In the context of maximum flat solution or the binomial approximation, okay, the bandwidth you aim to achieve isn't a parameters you can optimize directly. Okay, which means that earlier on I have mentioned also, by using this binomial, you basically cannot achieve your desired bandwidth. Basically, if you want to achieve certain bandwidth, you actually don't prefer to use this binomial. You can use Chebyshev. So therefore, this is what it means. If you want to achieve certain bandwidth, then don't use binomial. But for example, for this case, as illustrated over here, if this bandwidth isn't a parameters that you want to optimize, then you can actually consider to use this binomial approximation method. Okay, rather than that, it is determined by the number of sections and the ratio of the two impedance. Okay, so basically for the bandwidth, okay, basically will be depend on the number of sessions. Okay, earlier on, I have shown you a diagram. The larger number of sessions that you have, okay, the larger bandwidth you can actually also achieve. And basically, okay, on the bandwidth is also depend on the ratio of the two impedance that you actually want to match. Okay, essentially, okay, you will be constrained by the available space. Okay, the space is actually need to accommodate all this number of sessions. Okay, the more number of sessions, you are going to occupy more space. So basically, the constraint will be how much space you have in order to accommodate this multiple session of transformer. And also basically on the tolerance amount of loss, then you can actually use this so-called binomial, okay, which is the number of sessions and also the ratio of the two impedance, which control the bandwidth. The binomial transformer offer the exact solution for n equals to 1. Okay, so basically when you actually have n equals to 1, okay, so basically it will be just a quarter wavelength transformer. Okay, so basically this will be not necessary to use this method. Okay, on my previous video, I have also used this quarter wavelength impedance transformer in order to perform so-called impedance matching. So hence for 1, okay, n equals to 1, then I strongly suggest don't use this binomial transformer. Or maybe you can actually consider to use this binomial transformer when you actually has more than 2, n equals to 2. Okay, then this will be very useful. Why? Okay, because for higher order transformer, okay, basically this method only provide an approximation, okay, which means that you don't have the exact solution. You can only have some approximate solution. Okay, so this approximation deteriorate rapidly, especially when the mismatch between the source and load exceed 2 is equals to 1. Okay, when there is a high mismatch between the source and load, okay, then this method of binomial basically will not be accurate. So in short, for higher order, then you will not consider to use this binomial method, okay, because this method is an estimate method or approximate method. Okay, it should not be relied upon. Okay, it's important to note that this is only an approximation and should be avoided unless, okay, you are not worried about any degrade performance. Then you will use this binomial approximation. Okay, so basically why you want to use this is because the mathematical requirement for understanding this are very simple, which I'm going to go through soon. Okay, so these are the formula that you need in order to design this binomial multiple section transformer. Okay, so basically over here you will calculate the Ka coefficient, and this will be the design of the line impedance. Okay, this will be to calculate the numbers of bandwidth. Okay, those are the in yellow are some mathematical term. Okay, so basically you can see over here. Okay, so basically this CNN, basically the N, or I'm not sure what does this call, but in short, I have mentioned over here. So basically when you have this 3 with this exclamation mark, it will be equals to 3 times 2 times 1. Okay, so if it's 2, it will be 2 times 1. Okay, so basically it will so-called every number will go by 1. For example, if it's 4, it will be 4 times 3 times 2 times 1. So basically this is what it means by all this method here. Okay, so again, later on, I will have some example to go through this. Don't do well so much on this. But over here, I just want to show you all the essential design formula to design a binomial multi-section transformer. Okay, so basically later on you will see that I will actually make use of these 3 equations, and basically I will make use of some understanding of mathematical equation in order to solve the design of the multiple section binomial transformer. Okay, so basically let's go through an example in order to understand this better. Okay, so the example actually tasks us to design a 3-section, okay, which means that n equals to 3, binomial transformer to match a 50 ohm load to a 100 ohm transmission line. And we are also tasked to calculate the bandwidth for transmission. Okay, so basically this will be the maximum, okay, reflection coefficient, which is equals to 0.05. Okay, so basically you can see from here, this will be the load 50 ohm. This will be the transmission line. N is equals to 3. So I have 1, 2, 3. I have this 3-section of multi-section transformer using this binomial in order to achieve impedance transformer. Okay, so remember the 3 equations that I showed it to you earlier on. So basically this will be the first equation is to calculate the A coefficient. Okay, so basically this is to calculate the A coefficient. So basically, as I told you that N will be equals to 3, okay, because I have 3 sections of multiple sections, so I know that this will be 3. Okay, ZL will be equals to so-called the load. Okay, so basically the load will be 50. Z0 will be the transmission line, will be equals to 100. So therefore, from here, you can see that 2 minus 3, N equals to 3, and this is 50 minus 100, etc., which led me to calculate the A coefficient, which is equals to minus 0.0417. Okay, so basically I make use of the first equation that I have shared to you earlier on, okay, in order to calculate the A coefficient. Next, okay, I'm ready to use the second equation. Okay, the second equation is illustrated over here. So basically this will be the second equation. Okay, this second set of equation basically will allow us to design the line impedance. Okay, so let me show it to you. How can we actually calculate the so-called the 3-section? For example, for this example, I actually need to calculate the 3-section of multi-section transformer. So basically this equation will allow me to design the 3-section so-called line impedance. Okay, let me go through them step by step in order to understand better. Basically, this is the equation. Okay, for the first one that I'm going to do is n is equals to 3, and this small n equals to 0. Okay, so basically from this equation here, you can see that if this n is equal to 0, this will be Z1, as you can see from here. Okay, so basically n is equal to 0, so therefore this is 0. N again will be 0. So basically you can see that how I arrive this formula is because I'm actually tasked to do this n equals to 3 and the small n equal to 0, and therefore I get this equation. As for this equation here, Rn n equals to 0. Okay, again this big N will be minus 3. Okay, ZL, I hope you still remember. Okay, for the load will be 50. For the characteristics of the transmission line will be 100 over 50 plus 100. So basically this is how I achieve over here. And for this case here, this N is equals to 3 and this small and little n is equals to 0. And basically this is how I have calculated. Okay, I just want to make the discussion easier. Okay, so in terms of mathematics, I will not discuss that in full detail. Okay, but from here, you can see that I have derived all the different sets of equations from here. Okay, so therefore, if you have some issue on this, okay, let me know. Okay, I will be able to explain this further. But if not, okay, I just want to make this discussion shorter. Okay, so basically this n, for example, this n is 30. Okay, so basically this will be n. So basically, let's say this will be 3. So will be 3 times 2 times 1 over here. Let's say this is 0, then will be 3 minus 0. So this will be equal to 3. So from here, I can clearly see that this will be equals to 1, correct? So I leave how you derive this on your own, okay, but at this moment, okay, I feel that it's good that I will skip this part and go into the technical discussion. Okay, so basically this is how I get the first set, okay, which is the Z1 impedance for the first multi-section transformer. Okay, next, okay, so instead of n equals to 0, my small little n will be equals to 1. So basically when it's equals to 1, you can see here 1 plus 1 will be equal to Z2. This will be Z1. And then over here, this will be 1 plus R1 and then 1 minus R1. Okay, same for over here. So basically now it's 1. So this will be 1. My Bn will be still minus 3. So basically this part, okay, is intact. Okay, but for this case here, basically this will be equal to C13. Okay, because now n is equal to 1. And from here, I have done this second part of the multi-section transformer. Let's come to the last part of the multi-section transformer. Okay, nothing much. You can see from here now n is equal to 2. So 2 plus 1 equals to 3. This will be equal to 2. This r will be equal to 2. Here, this r2 here, 2 minus big letter n will be 3. So basically it will be 2 minus 3. Okay, this is intact and basically this is over here. So over here you can see that I have successfully derived the equation to design for the first session, for the second session, and the third session of multi-section transformer. Okay, let's go through a little bit more in discussion here. So this is what I have shown it to you on the previous slides here. So basically this part here, I have rewrite over here. Okay, so now I'm ready to calculate this portion here. Okay, so this will be 2 minus 3, 50 minus 100, etc. And then this will be C3 naught here. So basically from here, you can see that this will be equals to 1. Okay, you can punch your calculator. Okay, 2 to the power of minus 3 will be equals to 0.125. Okay, this part here, because 50 minus 100 will be minus 50. So therefore, my value will be minus. And then if you do this minus 50 divided by 150, you should be able to get this 0.3233. And this term is equal to 1. And from here, I calculate that my R0 is equal to minus 0.041666. Okay, so now I'm ready to calculate my first stage of impedance. Okay, so Z1 here. So basically, I will be calculate using this formula here. So Z0, okay, basically will be the characteristic impedance of the transmission line, okay, which is equals to 100. Okay, the question given to me. So 1 plus R0, okay, so basically R0 is equal to minus term here. So instead of plus, it becomes 1 minus 0.041666 here. So for the portion here, minus become positive. So therefore, this will be equal to 1 plus 0.041666. So from here, I have successfully calculated my first stage of multi-section transformer, which is 92 ohms. Coming to the second session here, so basically this will be the second session. Okay, the maximum n will be equal to 3. My small little n will be equal to 1. Okay, again, this set of equation is what I have derived from here. Okay, so I just put it over here. So I need to do some further analysis. Okay, I will be working on this set over here now. Okay, so this R1, 2 minus 3, everything is still the same, except this part here, okay, it slight changes. So basically, it will be using this C13 will be equal to 3. So from here, if you punch your calculator, okay, you should be able to arrive this minus 0.125. Okay, so again, from here, you can start to calculate your Z2 impedance. Okay, the Z1 will be equal to 92 here. Okay, and then this 1 plus R1 will be the value here. Okay, how you get, I guess you should be able to know. So from here, you calculate that Z2 will be equal to 71.55 ohm. So basically, this will be the second session of the multi-section transformer using binomial. Okay, so the last but not least, okay, the third session of the multiple session transformer. Okay, I believe you shouldn't have any difficulty. Okay, so basically for this part here will be basically what I have showed it over here. Okay, so what left I need to do is I need to understand this term here. So basically for this term here will be equal to 3, which means that this are exactly the same. So therefore I know my R2 will be equal to minus 0.125. As for here, this Z2 is basically what I have calculated earlier on, which is 71.55. So from here, I can calculate that for Z3, okay, the value will be 55.65 ohm. Okay, so basically this will be the third session of the multiple session transformer. So from here, I conclude that I actually successfully designed a binomial multi-session transformer. So from here, you can see that basically for this Z3, it will be having the value of 55.65 ohm. Z2 will be 71.55 ohm. And Z1 will be having this 92 ohm. So basically with this, you actually successfully design a multi-session transformer using binomial method. Okay, so hopefully this you will be more clear. Okay, before I continue, guys, I'd like to urge you guys to help me by like this video. When more of you guys actually like this video, okay, this video will have a higher chances to broadcast to a larger audience. So guys, help me by like this video. If you have learned something from this channel, please consider to subscribe to this channel. Last but not least, please remember to turn on your notification bell in order to receive more information from this channel. Once again, thank you so much for strong support. Okay, so next, okay, I'm going to show you another method, okay, which is used by Butterworth, how to design this binomial multi-session transformer. Okay, they basically make use of this table. Okay, but for this table here, okay, so this table only show data for ZL larger than Z0. Okay, since the design can be reversed, okay, which means that Z0 larger than ZL. Okay, the load and the source switch. Okay, this is what it means. Okay, but all this reflection coefficient value become negative. Okay, but this does not change the reflection coefficient because this is what we call a magnitude. Okay, the sign plus or minus is not so-called constant. So therefore, okay, basically you can also design this binomial transform basically by using this table. Okay, let me show you how to make use of this table to design this binomial transformer design using this binomial method. Okay, so let's take a look. Okay, this will be the same example that I mentioned earlier on. Basically, the example tasks us to design a 3-session, which means that n equals to 3. Again, it will be the same. Match a 50 ohm load to a 100 ohm transmission line. And then I have not done this. I have not calculated the bandwidth. Okay, so this part I will do it at the last part, how to calculate the bandwidth for this maximum reflection coefficient of 0.05. Okay, so basically we need to know how to make use of the table. Okay, so basically from here you can see that ZL over Z0. Okay, for this case here, the ZL, which is 50 over 100. Okay, so basically as the table mentioned here, as you can see from here, okay, they can be reversed. So basically for this case, if you take a look on this particular column here, you can see that, okay, the value is at least equals to 1 or maybe more than 1. So therefore, okay, I cannot have this scenario of using 50 over 100. So therefore, for this scenario, okay, I will be doing a reverse as it mentioned over here. It can be reversed and it will not affect the result, okay, because finally, okay, this reflection coefficient will having this magnitude, which means that we don't have any concern in terms of the minus. So therefore, for this particular case, I will use 100 divided by 50, which is equals to 2. Okay, so basically I have this ZL over Z0 is equals to 2. So which table to look at? Okay, let me show it to you. Okay, so this will be the n equals to 3. Remember, we need to design 3 multi-section transformer. So basically, I will select this so-called table. And earlier on, I have shown it to you the ZL over Z0, which is equal to 2. So therefore, I will select all these data. Okay, in short, Z1 over Z0 will be equals to 1.0907. Z2 over Z0 will be equals to 1.4142. Z3 over Z0 will be equals to 1.8337. Okay, which is shown over here. Okay, so basically this is what I have so-called just copy from the table that I have shown it to you earlier on. So basically I just copy this value here, okay, over here. Okay, but because, okay, we do a reverse, remember I told you that we do a reverse. Okay, so instead of 50 divided by 100, I actually use this 100 divided by 50. And once I do this, okay, I must switch the position of this value here. So over here, you can see that I actually switch the value. Okay, so basically this Z1, okay, basically will be equals to 1.8337 now. I switch this to Z1. Okay, Z2 will be still the same, will be 1.4142. Okay, 3 will be equals to 1.0907. Okay, so basically the Z0, okay, basically for this case here, the Z0 will be equals to 50. Can you still remember? This is 100 divided by 50. So basically for this Z0, it will be equals to 50 over here. Okay, so therefore, how can I actually get all this number here? So basically, I can use this 1.8337 multiplied by 50. I should be able to get this 91.7 ohm. And if I use this 1.4142 multiplied by 50, I should be able to get this 70.7. And last but not least, if I use this 1.0907 multiplied by 50, I should be able to get this 54.6 ohm. Okay, so basically, this is another method. How can I actually calculate the 3 multi-section transformer using this binomial method? Okay, so basically earlier on I have also calculated. Okay, let me share what I have calculated earlier on. So basically this is what I have calculated earlier on. Okay, instead of using the table, okay, I use all the formulas. You can see that the answer that we actually arrive is pretty close. Okay, so I think you must accept some certain difference. Okay, so basically you can see that the difference is around maximum only 1 ohm. So basically it will not have any big drastic difference. But over here, I show it to you the two methods to calculate the binomial multi-section transformer example. Okay, firstly, I use the convention formulas to calculate, and basically I arrive at all these answers. So next, I actually use this so-called using a table. Okay, so basically, if you want to know more about this table, you can look at David Poza textbook. Okay, so basically, this is how they calculate this. And like what I mentioned earlier on, all these values look almost the same. So from here, you actually have successfully designed 3 sessions of multi-session transformer using binomial approximate method. Okay, so hopefully this is clear now. Okay, so let's move on to the last session, which is to calculate the bandwidth. Okay, so basically this is the formula to calculate the bandwidth. Okay, the maximum reflection coefficient will be equal to 0.05. And these are all the value here. So basically from here, I will be able to calculate the bandwidth. Okay, keep this in mind. Remember to change all these to radian. Okay, remember don't use degree. Change all these to radian because you before you actually plug all the numbers and calculate. So from here you will be able to calculate that the bandwidth is equal to 0.713, and basically you can so-called the bandwidth, which is 71.3%. So basically just want to give you some numbers comparison between a lambda over 4 transformer versus 3 session of multi-session transformer. Okay, for a single quarter wave transformer, for example, for this case here, the typical bandwidth is about 6%. Okay, but over here, if you use 3 session using this binomial to calculate, to do this impedance transformer, you can see that the bandwidth is so much larger, which is 71.3%. Okay, so with this, I'd like to end my discussion. Please help to like and subscribe. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.